21.2 Temperature and hypoxia. Our body is designed to stay at a constant temperature of 36.9 degrees. This is also known as homeostasis. One of the reasons why we try to keep our body at this temperature is because it's the optimal temperature for enzymes to function. They act as a biological catalyst, and without them we would die. If we become too hot, then these enzymes denature, and if we get too cold, then they slow down. When we exercise, we perform at our best when the temperature isn't too hot or too cold. Figure 1 shows that if we slightly overheat, then we start sweating. If we become even hotter, then we might faint or vomit, and if we become severely hot, then we can go into shock, develop brain damage, or even die. If we become slightly cold, then we begin to shiver. If we get colder, then we can become delirious or hallucinate, and if we get even colder, then we can die. In order to control our body's temperature, the negative feedback loop is used. It consists of the hypothalamus, which is found in the brain, thermoreceptors, and effectors. If the body becomes too hot or too cold, then the thermoreceptors send a signal to the hypothalamus. The hypothalamus sends an impulse to the effector, which causes a response to a change in the temperature. For instance, if the body becomes too hot, then the effectors might cause the body to sweat, or if the body becomes too cold, then it will be told to shiver. There are three mechanisms which are used to reduce high temperature in the body: sweating, flattening of hairs, and vasodilation of the veins. Sweating helps heat loss by evaporating water from the surface of the skin, which helps it to cool down. The muscles will relax and cause the hairs to flatten, which will increase convection by preventing air from being trapped. Capillaries help to move blood closer to the surface of the skin, which helps us to lose heat via convection and conduction. Blood vessels also increase in size, which helps them to lose heat more effectively, because there is a bigger surface area for convection and conduction to occur. If a person is running the Marathon des Sables, then the body will use these mechanisms to prevent it from overheating. When we exercise, we sweat, which causes us to lose water. If we lose too much water, then we become dehydrated. Dehydration is much more common when exercising in the heat, because our body tries to sweat more to keep us cool, but instead we become increasingly dehydrated. Dehydration can be fatal and can lead to heat stroke or hypothermia if nothing is done to cool the person down. Figure 2 shows how to treat someone who has heat stroke. They need to be lying down, drink fluid, have cold things on their body, a fan, and their feet need to be elevated. Dehydration can lead to hypothermia, which is where the body is producing more heat than it can dissipate. People who exercise in the heat have a higher chance of developing hypothermia. There are two main problems which cause a decrease in sporting performance in the heat. The first one is an increase in core temperature, hypothermia, which can cause a decrease in muscular endurance. This prevents the body from being able to create repeated contractions, which is why aerobic performance decreases. The second is dehydration, which reduces VO2 max, which means that the body can't use oxygen as efficiently. This would be particularly noticeable in long aerobic or 400 type events, which require the body to use a lot of oxygen. This is why professional athletes either train or go to where they are competing to acclimatise. Athletes competing in Rio went to Rio to train before their races. Also, some athletes such as Mo Farah use heat chambers to get used to exercising in the heat. We know that the body likes to keep a constant internal core temperature. If our body is losing more heat than it is producing, then our internal core temperature will begin to go down. If our core temperature goes down below 35 degrees, then we will develop hypothermia. There are three types of hypothermia. Acute hypothermia is when we rapidly lose heat, for instance, getting into very cold water. Exhaustion hypothermia is when the person is too exhausted to generate heat. For instance, people who get stuck up mountains are often so exhausted that they can't create heat for their body to stay alive. Chronic hypothermia is when the body slowly loses heat. This happens to people who are elderly and don't have central heating, or homeless people who live in cold weather. This chart shows the stages of hypothermia and what we can do about it. Hypothermia causes the following changes to occur in our body. It lowers our breathing rate, it lowers our blood pressure, it lowers our heart rate, and there's a decrease in our cellular function, and it can cause us to become drowsy. If we are exercising in extremely cold temperatures, then our body has mechanisms to keep heat inside of the body, which include vasoconstriction, straightening of the hairs, shivering, and the glands to decrease secretion. For instance, skiers who are up a mountain might experience these mechanisms to help their body stay warm. Shivering uses the skeletal muscles to create contractions, which produce heat. Our body reduces sweating to conserve heat by reducing the amount of evaporation on the skin's surface. The capillaries, which are close to the skin surface, vasoconstrict, which makes them smaller and in turn reduces the amount of heat lost. Temperature receptors in the skin detect the temperature becoming too cold. They send a message via an impulse to the hypothalamus in the brain. The hypothalamus can also detect changes in temperature of the blood through its own receptors. The hypothalamus tells the effector, which are in the sweat gland and muscles, to take action. There are three factors which affect sports performance in cold temperatures. The first one is a risk of injury, such as a tendon or muscle tears. When we get too cold, our muscles stiffen and become less pliable. If we move them vigorously, then we can get injured. Exercising in the cold can also lead to hypothermia, which can cause an athlete to become fatigued, disorientated, and lose coordination. Miriam Sandad et al. Conducted a study into the thermoregulatory responses in cross-country skiers. They found that even a slight decrease in skin temperature affected muscular sporting performance, and they referred to other studies which showed that big temperature differences had a very significant effect on time to exhaustion. Usually, athletes compete at sea level, and the partial pressure for inhaled air at sea level is known as normoxia. Athletes train at altitude because the air pressure is lower, so less O2 gets into their lungs and blood. This is called hypoxia. This stops hemoglobin from getting as saturated as it would at sea level. As a result of this, the body creates more red blood cells to cope with a decrease in the amount of oxygen. This gives athletes who spend time at altitude an advantage because when they return to sea level, they have created extra blood cells, which allows them to compete harder for longer. Altitude training is mainly beneficial for sports which require the athlete to work aerobically, often for long periods of time. There are two different types of hypoxia, which are normobaric and hyperbaric. Normobaric is fake altitude. This is when an athlete spends time in an oxygen tent at sea level to create the same physiological responses of spending time living at altitude. For instance, Kendrick Monk, a 200-meter freestyler, slept in an altitude tent simulating 1,850 meters above sea level before the Beijing Olympics. Hyperbaric is real altitude. This is when the athlete is actually living at altitude. For instance, Kenyan distance runner live and train at altitude, so they have more red blood cells for when they return to sea level. People believe that there is less oxygen in the air at altitude than at sea level, but actually the air at altitude contains 21% of oxygen, which is the same at sea level. The difference is that the air is thinner because the pressure is lower. This means that the lungs breathe in less air overall, and therefore less oxygen. Altitude tents achieve the same outcome by keeping the pressure the same, but reducing the amount of oxygen in the air. For example, reducing the amount of oxygen in the air from 21% to 15% is equivalent to being at 3,000 meters. At sea level, the air is sucked into the lungs because of the low partial pressure of oxygen in the lungs, and a high partial pressure in the atmosphere, the oxygen then goes into the alveoli and diffuses into the capillaries because there's a high partial pressure in the alveoli and a low partial pressure in the capillaries. The oxygen associates to the hemoglobin where it becomes fully saturated. The hemoglobin is then transported to the muscles in the blood. The hemoglobin dissociates some of the oxygen for it to diffuse into the muscles. CO2 diffuses out of the muscle wall, where the partial pressure of CO2 is high, and it associates to the hemoglobin in the blood, where the concentration of CO2 is low, to form carbaminohemoglobin. This is transported in the blood back to the capillaries by the lungs. The carbon dioxide diffuses from the high partial pressure in the capillaries into a low partial pressure in the alveoli in the lungs and is exhaled out. One of the first acute responses of the body to hypoxia is hyperventilation. Our body is used to normal sea level amounts of oxygen, and it's a shock for the body having less oxygen. As a result, our breathing rate increases to cope with the diminished amount of oxygen. Kendrick Monk often woke up in the night gasping for air because his body didn't have enough oxygen. Another immediate response is tachycardia, which is where the resting heart rate increases. This is another way the body tries to increase the amount of oxygen by pumping more blood around the body to transport the oxygen from the lungs.